In this lesson, we're going to get into a little bit of the history of why we think, how we know that there are atoms. And so we're going to go through some of the development, how we got to the point of knowing what we know now about atoms. And it goes all the way back to the Greeks. So we're going to talk a little bit about history for a second. Greece, surely you studied that in your world history classes, you know a little bit about it. So it says not the history of the atom because the Greeks did not discover the atom. It's important that you understand that the Greeks did not discover the atom, but the idea of the atom sort of originated with the Greeks in a way that we're going to begin to see here. And so in you've heard the earth, wind, fire, and air. Those and water. Where's water? Why isn't water in there? Air and wind are the same thing. What's going on? Well, I stole this. So, oh, I didn't steal it. Shoot. Oh well. So we're going to go back to the originals, Democritus and Leucippus. I'm sure I'm not pronouncing that right, but it doesn't really matter. So Democritus is the person we're going to talk about. And over on the right, you see there his model of the atom. We'll talk about that in a second. Let's talk a little bit about him as a person first. First, he was a philosopher. He was not a scientist. So this predated the scientific method, and they had not really come up with the idea of testing and experimentalism and empiricism. Those ideas weren't really quite there yet. And so what philosophers did, they weren't really scientists, although some philosophers did some good science, but that wasn't really the mode that philosophers worked in. They would kind of sit around and they would come up with what they thought was the best idea, and they wouldn't necessarily go about a systematic way of everyone agreeing whether that solution was right or not. They weren't scientists. Democritus wasn't a scientist. The idea of democracy, it always comes up. He was one of the people fairly early on who kind of embraced the idea of democracy, people ruling themselves. But he, even though the names sound a little like, they have nothing to do with one another in terms of the names. And this is what we want to get to. This is the important part of this slide. And that is that the idea of atomos is the word where atom comes from. So atomos means indivisible. And what that means is, so tomos is like a verb, I don't know, like to be able to cut. So in Greek, tome has to do with cutting things. And just like in atheism or agnosticism or asexual, that a prefix means no, it means you can't or not. And so atome, not cut. So that's where we get the idea of indivisibility. So atom literally means uncuttable, means indivisible. And so that's where the word atom comes from. And the thing to understand about Democritus is he did not provide any experimental evidence for his ideas. They were just kind of things he thought. And so that last little word doesn't matter so much, continuous versus discontinuous. Basically, the idea is there some kind of smallest thing you can cut matter into, yes or no? Continuous would say no, discontinuous would say yes, there is a smallest piece. And so over on the right, we're going to start with, so this is Democritus's model of the atom. It's just kind of this bland sort of idea of there's this tiny solid piece you can't cut. Even the fact that it's spherical isn't necessarily something that he would have attributed to all atoms. He said they can't destroy them, they're nice and solid. So, which leads us then to the next guy we're going to talk about is Robert Boyle. Now, Robert Boyle was one of the early empiricists. He actually would run experiments and try to measure things. And so he gave us probably the idea of elements that we continue to use today, generally speaking, is that an element is a substance that you cannot break down any further. He would have said that earth wasn't an element because you could break it into other things, that water wasn't an element because you could break it down into other things. And that's the basic purpose of this slide, to kind of introduce the idea of elements, which we got from Robert Boyle. And I didn't talk about this, but and give a date on Boyle, but the Greek people were talking about that was about 2,400 years ago, whereas Boyle would have been only something like 8 or 500 years ago in the 1600s. And so this is quite a bit later than the Greeks. So we're quite a bit further along here. So I'm going to introduce 3 laws here. You can stop and pause the video and write these down if you want, but we're going to talk about each one of them on its own slide. I'm just kind of laying them out there in case you want a list, but you don't need to pay attention to these right now. We're going to talk about them. We're going to say what all these things mean in the later slides. So if you don't get it all down right now, that's fine. So the law of conservation of matter was first articulated by Antoine LaVoisier. I'll tell you what, matter is neither created or destroyed. Lavoisier was a Frenchman. He lived during the French Revolution, and the fact that he was a person who had the means to sit around and contemplating the ideas of laws of conservation of matter tells you that he was not long for this world. If he was a nobleman, and he had money, he had wealth, and he lived during the French Revolution. So he, as many of that time and that circumstances did, ended up getting the close shave, as they say, with the guillotine. But before he did, he said he came up with this law. Now, a law is not something that explains why something is true, but it just finds a pattern. So this law, this pattern that he found in nature, was that he found that you never create or destroy matter. If you have something, let's say, enclosed in a big bell jar, and you do anything inside of the bell jar, you run reactions, you burn things, whatever, the total weight inside the bell jar before and after the change will always be the same. And that was the law of conservation of matter. It means that, simply put, as it says there, matter cannot be created, matter cannot be destroyed. It just is. You can sort of change it, but you can't change how much there is. Get to the second law now, the second pattern that was observed. So this is kind of the theme here. We find that a lot of these early scientists were finding patterns. They couldn't explain them, but they found a pattern. And later on, we're going to put these patterns together into a cohesive idea of what's going on. And so Joseph Proust, Proust came up with the law of definite proportions. And so what does that say? Well, it says that each compound, now a compound is something with more than one element, like water is a compound. Water has H2O, 2 H's and an O. We know that now, but it has, it's not a mixture. They've chemically combined into one new thing, water. And so that's what a compound is. And he said that a compound has a specific ratio comparison by weight of the two or more elements. And so it's a mass ratio. So for example, for water, he found that for every any sample of water you get from anywhere, and if you're able to break down that water, which isn't in elements, you can break it down into simpler substances. You can break it into 8 grams of oxygen for every 1 gram of hydrogen. So however many grams of hydrogen you're able to get out of that water, you're going to get 8 times as many oxygen. So if you get 4 grams of hydrogen, you're going to get 32 grams of oxygen. It's always an 8-to-1 ratio. And so that's the example for water. But for any compound out there, if you break it down into its component parts, what he found was it was always a specific ratio. It wouldn't be like 8-to-1 one day and then 3-to-1 the next. Now, different compounds have different ratios. Hydrogen peroxide might be different than water, might be different than salt. All these different things, when they break out, they don't always come out in 8-to-1, but they always, whatever the compound is, it always maintains the same ratio. Which brings us to our third and final big new law, the law of multiple proportions. The law of multiple proportions was cited by a guy by the name of John Dalton. We're going to hear a lot more about him in a minute. But he found that sometimes you have different compounds that they're different substances. They're not the same thing, but they're made of the same elements. And the example that we give always for this is water and hydrogen peroxide. Now, I think we all know what water is, and hydrogen peroxide, you're probably familiar with it also. It comes in a little brown bottle from Walmart. It's bubbly. We put it on cuts and things it's an antiseptic. And so they're different. Like water doesn't sit around and bubble for no reason like hydrogen peroxide does. One's fizzy. They have different properties. They're different things, but we do know they're both made out of hydrogen and oxygen. And what Dalton discovered was this idea that if you have two things like water and hydrogen peroxide, the ratios between the two compounds so water is 8:1. We just talked about that. That was the law of definite proportions. And as they studied hydrogen peroxide, they found out that it was 16:1. So water is 8:1, hydrogen peroxide 16:1. You see a pattern there. That's 8:1 pattern versus the 16:1 pattern. What do you know about 16 and 8? Well, they're direct multiples of each other, or one is a multiple of the other. And so what he found was in just about any case where you have these sorts of different compounds made of the same elements, one ratio will always be an exact ratio of the other. So like 8:1 here, 16:1 here. So for example, if a different compound had a 4:3 ratio, then maybe a related compound would be an 8:3 or a 16:3 ratio. They would always be these simple multiples of one another. And so that was the third and final law that we're going to delve into as we get into the atomic theory here. And I'm gonna go ahead and pause the video here. I'm going to stop here. We're not really done. We've only told half the story, but what we're going to see next is how does I'm going to break it into multiple videos in case I need to for future reasons. But we're going to see in the next video, well, how John Dalton actually takes these three ideas: the law of conservation of matter, the law of definite proportions, and the law of multiple proportions, and he's going to kind of form it all into one cohesive explanation, the theory of the atom.